Imagine you have a small backpack that can hold only a limited weight, say 10 kilograms, and you are at a toy store with many different toys. Each toy has its own weight and fun value. You want to pick toys that give you the most fun without making the backpack too heavy. If you try every possible combination of toys, the number of possibilities grows explosively, 2 to the n for n toys, and you will quickly run out of time. The 0/1 Knapsack Dynamic Programming (DP) approach is like a clever notebook where you write down the best fun you can achieve for every possible weight from 0 to 10 kilograms, building the answer step by step. This avoids rechecking the same choices over and over, making the problem solvable even when there are many items. We are given n items indexed by I equals 1 to n, weight w sub I a positive integer for each item, value v sub I a positive integer for each item, and a knapsack capacity c a positive integer. We must choose a subset S, which is a subset of the set from 1 to n, such that the total weight sum over I in S of w sub I is less than or equal to c, and the total value sum over I in S of v sub I is maximized. The decision variable x sub I belongs to the set 0 to 1, indicating whether item I is taken 1 or not taken 0. Maximize the sum over I from 1 to n of v sub I times x sub I. Subject to the sum over I from 1 to n of w sub I times x sub I being less than or equal to c. And x sub I belongs to the set 0 to 1 for all I. This is the classic 0-1 knapsack problem because each item can be taken at most once, either 0 or 1. Explanation: to see why DP works, look at the last item n. Any optimal solution either takes item n or leaves it. If we do not take it, the best value we can get is exactly the optimal solution for the first n-1 items with the same capacity c. If we do take it, we must pay its weight w sub n, leaving capacity c minus w sub n for the first n-1 items, and we gain value v sub n in addition. Therefore, the optimal value v of I, c for the first I items and capacity c satisfies the recurrence. V of I, c equals 0 if I equals 0 or c equals 0. V of I minus 1, c if w sub I is greater than c cannot fit item I. Otherwise, the maximum of v of I minus 1, c and v of I minus 1, c minus w sub I plus v sub I. This relation shows the problem has optimal substructure. The solution to a larger problem is built from optimal solutions of smaller subproblems. Explanation: we fill a table dp 0 to n, 0 to see where dp of IC stores v of IC. The bottom-up method starts with I equals 0, no items, and c equals 0, empty knapsack, and sets those cells to 0. Then we iterate I from 1 to n, and for each I, iterate c from 0 to c. Using the recurrence, we compute dp of IC in big O of 1 time, so the whole table is built in big O of n times c steps. The final answer is dp of nc, the best value we can achieve with all items and the full capacity. The table can be visualized as a grid where rows are items and columns are weight limits. Each cell tells you the maximum fun you can get if you are allowed only the items up to that row and only that much weight. Example: suppose 3 items, w, v equals 3, 4, 4, 5, 2, 3, and c equals 6. The DP table will show that the best value for capacity 6 is 7, items 1 and 3. Notice that to compute DPIC, we only need the previous row DPI minus 1. Therefore, we can keep just one one-dimensional array of length c plus 1, updating it from right to left so that dpc minus wi still holds the value from the previous I. Pseudocode: let dp from 0 to c equals 0. For each item I equals 1 to n. For c equals c down to wi. dpc equals the maximum of dpc, and dpc minus wi plus vi. Now dpc always holds vic after processing I items. This reduces memory from big O of n times c to big O of c. A rolling array is the same idea but using 2 rows, previous and current, when you prefer left to right updates. The analogy is like having a single notebook where you overwrite old entries, but you read the old numbers before you erase them, ensuring you don't lose needed information. After the DP finishes, we know the maximum value, but we may also want to know which items give that value. Starting from dp of n and c, we walk backwards. If dp of I and c equals dp of I minus 1 and c, item I was not taken. Otherwise, item I was taken, we record I and set c equal to c minus w sub I, then continue with I minus 1. When using the 1D version, we keep a copy of the table, or we store a choice Boolean matrix during the fill phase. The backtrack yields the exact set of items that achieve the optimum, just like retracing steps on a treasure map, to see which clues you followed. Example continued from dp of 3 and 6 equals 7, we see dp of 3 and 6 not equal dp of 2 and 6, which is 5, so item 3 weight 2 value 3 was taken. New capacity 6 minus 2 equals 4. Now dp of 2 and 4 equals dp of 1, and 4 equals 4, so item 2 was not taken. Finally, dp of 1 and 4 not equal dp of 0, and 4 0, so item 1 was taken. The optimal set is items 1 and 3. The dp algorithm runs two nested loops, one over the n items and one over capacities 0 to c. Each step does constant work, so the running time is theta of n times c. This bound is tight because every cell of the table must be examined in the worst case. The space needed is theta of n times c for the full table, but with the one-dimensional optimization, it drops to theta of c. If the number's weights values are very large, c can be huge and the algorithm becomes pseudo-polynomial. Polynomial in the numeric value of c, not in the length of the input, which is log c. That explains why the knapsack problem is NP hard in general, yet dp gives an exact solution for moderate capacities. In practice, for n approximately 10 to the power of 4 and c approximately 10 to the power of 5, the algorithm runs in a few seconds on modern computers. Real-world knapsack problems come in many flavors. Bounded knapsack. Each item type is available only a limited number of copies. For example, you have 3 copies of a particular toy. The dp can be adapted by treating each copy as a separate 0-1 item or by using a more clever binary splitting technique. Unbounded knapsack. You can take unlimited copies of each item, for example, unlimited supply of small candies. dp of c equals max over I such that w sub I is less than or equal to c of dp of c minus w sub I plus v sub I. The inner loop runs forward, allowing reuse of the same item. Multi-dimensional knapsack. Instead of a single weight limit, there are multiple resources, for example weight and volume. dp of I, c sub 1, c sub 2, and so on. Big O of n times c sub 1 times c sub 2, and so on. The same optimal substructure idea applies, but the problem quickly becomes harder as dimensions grow. These extensions illustrate how the core dp insight, break a big decision into smaller overlapping decisions, remains powerful across many practical packing, budgeting, and resource allocation scenarios.